Hey everyone, my name is Patrick Sumner, and today I'll be discussing the Dallas-Fort Worth microclimate and surface ozone variability under different drought conditions. DFW is classified as a humid subtropical climate with warm summers and a wet fall and spring season. The urban heat island is a phenomenon that occurs due to temperature differences between urban and rural areas. Ozone at the surface is a harmful air pollutant and is formed through the photochemical reaction of nitrogen dioxide, sulfur dioxide, and various volatile organic compounds released from automobiles. It's been documented that an increase in temperature can cause ozone concentrations to increase. DFW is the fourth largest and fastest growing metroplex in the United States, with its population nearly doubling from 1990 to 2020. With this information in mind, it forms two main objectives. First, there is a need to understand how the microclimate responds to different drought conditions. Second, assessing how drought conditions affect the temperature, nitrogen dioxide, and ozone will allow more informed decisions and preparation to be made towards both human and environmental health. To do the study, I collected hourly data from stations that are monitored by the Texas Commission on Environmental Quality. I calculated the urban heat island values, which is done by determining the temperature difference between an urban and rural station. I utilized CAM 60, which is in downtown Dallas, and CAMS 1044, which is in the countryside in Ellis County. Both stations are at approximately the same elevation, which is important to keep constant when quantifying the urban heat island. I did the calculation at solar noon, which is when solar radiation peaks across July from 2008 to 2023. I used the Palmer Drought Severity Index as an indices for soil moisture. When correlating the temperature, nitrogen dioxide, and ozone, I did so with the maximum daily 8-hour average. I calculated this for all the stations and averaged them all together to get one single value for each year. This graph shows the average urban heat island value at solar noon in July from 2008 to 2023. Each point is color-coded to the soil moisture content, with dark green being highly saturated and dark brown being very dry. There are three key takeaways from this graph. First, in wet conditions, the urban heat island tended to be above 1 degree Celsius, but during dry conditions, it tended to be below 1 degree Celsius. The temperatures of urban areas are typically always greater than that of rural areas because concrete and other urban materials have a greater thermal emittance. In dry conditions, rural areas warmed up even faster, and though did not surpass the temperatures of urban areas, it did decrease the temperature difference. Second, during extreme drought in 2011-22, the urban heat island decreased by at least 2 degrees Celsius relative to the conditions leading up to it. The surface roughness of a city plays a role in the urban heat island during extreme heat. When looking at the land cover map, we see that Camp 60 is in the urban built-up area, which is aerodynamically rougher than the low-lying grasslands and croplands of Camps 1044. In extreme drought, heat is more easily advected on smoother surfaces as opposed to rougher surfaces. Furthermore, when warm air reaches rough areas like buildings, rather the temperature being advected horizontally, the heat is convected vertically up into the atmosphere. Finally, the man-candle test revealed a significant correlation of an increasing urban heat island value over time. However, my study is only over 16 years, so it is difficult to make long-term climate conclusions without decadal data. These contour plots are the absolute values of temperature, nitrogen dioxide, and ozone at CAM 60 and CAM 1044. As expected, temperatures are greater at CAM 60. The nitrogen dioxide peaks slightly before sunrise and after sunset, and is significantly greater at CAM 60 due to more emissions from automobiles. Nitrogen dioxide dissociates in sunlight, and a single oxygen atom then reacts with oxygen to form ozone, which peaks in the afternoon hours. Ozone did have increased concentrations at CAM 60, likely due to greater nitrogen dioxide. Pearson correlations for the maximum daily 8-hour averages of all three variables revealed two significant correlations. First, temperature accounts for about 19% of the variability of ozone, and 41% of the variability of ozone is due to nitrogen dioxide. Furthermore, ozone concentrations increase during dry conditions, and it's been proposed that with an influx of water vapor, the formation of the hydroxyl radical reacts with other air pollutants and serves as a sink for ozone formation. Sources of this moisture could be the Bermuda high pressure system in the Atlantic Ocean or the Great Plains low level jet, both of which transfer water vapor from the Gulf of Mexico to DFW. Thank you.